Hello and welcome back, fellow path integrators. Today's topic, the tunnel effect, alpha decay, and a beautiful integral that we will solve with 3 substitutions. Let's go! So, the tunnel effect is one of the weirdest effects that quantum physics has to offer. Despite its weirdness though, it has an immense practical application. It explains how the radioactive alpha decay works. So let's put the alpha particle into the potential of a nucleus. It moves inside of the radius of the nucleus, but it has no way out. Classically, it would need an immense amount of energy to get over the top to the other side of the potential. But the alpha particle is not classic. It's quantum, and it can just tunnel through the potential wall. How this works has been described by George Gamow, a Soviet physicist born in Odessa, Ukraine, who fled from the Stalin regime to the US. And he not only discovered a formula to describe the tunnel effect, which is known as the Gamow factor, where A and B, the limits of the integral, are the turnback points of a particle trapped in the potential. V of x is the potential itself, dependent on the position x, and E is the entire energy of the particle. No, he also worked on nuclear physics of the early universe, and he predicted the existence of the cosmic microwave background 16 years before it has actually been discovered. But back to the alpha decay and the integral. So we have the nuclear potential, and we have the turnback points, which are R, the capital R, which is the radius of our nucleus, and Rc, which is on the other side of the potential, and is determined by gamma and E. E is the entire energy of the particle. Gamma is a constant that comes out of the Coulomb potential of the potential wall that the alpha particle has to cross through. So gamma is 2 times z times E squared divided by 4 pi times epsilon 0. So with that knowledge, we can plug in all the things into our formula for the Gamow factor. So A and B will be the turnback points of the nuclear potential, capital R and Rc. V of x will be gamma divided by R, dx turns to R because we're having a radial symmetric problem, and the entire energy E will stay the same. So this is how our formula will look like, where gamma divided by R is the potential V of R, and as you can see, the integration variable also changed. So when we take a look at this exponential, it looks quite difficult. And before we can think about how to solve that, we need to solve the argument first. So this means we need to solve the integral. And this will be our today's task. What we're gonna do is we define this whole thing, 2 divided by h bar times the integral, as g. So our transition probability will be e to the power of minus g. How are we going to solve this integral? Well, first of all, we're going to plug in what we know for gamma, because Rc is gamma divided by E, which means that gamma is E times Rc. So by plugging that in, we will see that in our square root there are 4 e's, and we can extract that out of the integral. So our integrand simplifies itself a little bit, and we can rewrite the fraction inside of the square root as well, and then we have Rc minus R divided by R in the square root, and this we can divide up into 2 fractions. So we have the square root of Rc minus R divided by the square root of R. And now comes the first substitution that we will perform. What we will say is that u, our new substitution variable, is equal to the square root of r, which means that the derivative of u with respect to r is 1 divided by 2 times square root of r. This, on the other hand, means that dr transforms to 2u times du, and we also have to substitute the limits of our integral, so u of rc becomes the square root of rc, and the other limit, the capital R, becomes the square root of r. So let's plug that in into the integral, and we will see that the u will cancel each other out, so we will stay with the square root of rc minus u squared, and we can also rewrite that by extracting the square root of rc out of the integral. And then we will get the following thing. The square root of 1 minus, in brackets, u divided by square root of rc, and the whole thing in brackets. And how this helps us is because if we substitute that fraction u divided by square root of rc by something, we could then maybe see that this is pretty similar to the formula 1 minus sine squared inside of the square root, and this will just give us the cosine, or we can also plug in cosine instead of sine. So what we will do now is we will attack this integral with our second substitution. Our second substitution is the following. Z is equal to u divided by the square root of rc, which means that the derivative of z with respect to u is 1 divided by the square root of rc. This, on the other hand, means that du transforms to the square root of rc times dz, where rc is just a constant. And this means that our limits of the integral, the square root of r, turns to the square root of r divided by rc, and the other limit turns to 1 because we have the square root of rc divided by the square root of rc. So let's plug that in into the integral, and we will get this, which looks so much simpler. Well, the limits of the integral, they look a bit complicated, especially the one with the square root of r divided by rc. The one does not look so complicated, but the integrand looks nice because now we can do our third substitution. We can say that z is equal to sine of theta, which then means that dz with the derivative of dz with respect to theta is cosine of theta, and this means that dz transforms to cosine of theta times d theta. But we also have to substitute the limits of the integral now, and we will do that by doing it reverse. So theta of z is the arcsine of theta of z, which means that theta of the limit square root of r divided by rc, the bottom limit, is the arcsine of the square root of r divided by rc. So the bottom limit of our integral just got a little bit more complicated. What about the top limit of our integral? Well, theta of 1 is equal to arcsine of 1, and the arcsine of 1 is pi over 2. It's a bit simpler now. Okay, how does our integral look right now? Well, we have the square root of 1 minus z squared, we put in the substitution, and what we will get is the square root of 1 minus sine squared theta times the new integration variable, infinitesimal element cosine theta times d theta. And 1 minus sine squared of theta, that's just cosine squared of theta. The square root out of that is cosine of theta, which means that our integral will be over cosine of theta squared with the super weird limit, arcsine of square root of r divided by rc and pi over 2. And now we just need to plug in what we know is the integral of cosine squared, which is 1/2 times in brackets sine of theta times cosine of theta plus theta. Of course plus a constant, but we won't need the constant here. So let's plug that into the integral, and what we will get is the following. So we have 2 times rc divided by h bar times the square root of 2me, which is outside of the brackets, outside of what is happening in the integral. And the solution to the integral itself is pi over 2 minus the square root of r divided by rc times cosine of arcsine of the square root of r divided by rc plus the arcsine of the square root of r divided by rc. When you take a look at the cosine of arcsine, we can rewrite that by saying that the cosine is the square root of 1 minus sine squared. And this will lead us to this. So the cosine of arcsine of this square root term changed to the square root, the big square root of r divided by rc times in brackets 1 minus r divided by rc. And the whole term that you can see here is that g that we have defined before in this video. And this g, we plug that into the exponential, and then we get our probability for a particle tunneling through the potential wall of a nucleus, depending on the radius of the nucleus, the energy of the particle, and some constant factors that determine the Coulomb potential. So I hope you liked solving this integral together with me. I hope you could learn something new about physics, about the tunnel effect, about alpha decay, maybe even a little bit about history. And if you liked this video, leave a like. Let me know in the comments how you think about it, what else you would like me to cover, maybe new ideas for new videos. And yeah, subscribe to my channel. That would help me a lot with the algorithm. I mean, you know, guys, the algorithm. Anyway, so it was a pleasure to do that with you. See you in the comments. See you in the next video. Bye.